Welcome to another episode of Mr. Avila Physics. Today we're going to be talking about friction force. Friction force is known as the force that opposes motion. Since this force opposes motion, that means that the direction of friction force will always be in the opposite direction of the motion of the object. If the object is moving right, then friction force will act to the left. If the object is moving south, then friction force will act north. Okay? Now, friction force depends on two things. All right? The first thing is the type of surfaces that are being in contact, okay? And how rough the surfaces are. For example, if you're trying to drag a cardboard box on hardwood floors, it's going to be easier than if you're trying to drag that same box through a carpet. Right? Carpet's a little bit more rough, so it'll be harder to move the box on the carpet than on the floor. Okay? And the other thing that friction depends on is the harder that these two surfaces are squished together. Right? For example, you're trying to drag the box through hardwood floors, and then your brother jumps inside the box, and now it's going to be harder to push that same box, right? Because now the box and the floor are being squished harder together. Now, the roughness of the surfaces is known as the coefficient of friction. Okay. Now, this coefficient is a numerical value that is given to surfaces of different roughness just to have like a scale of how rough a surface is. For example, ice would have a low coefficient of friction, while sandpaper will have a high coefficient of friction. Okay. Now, coefficient of friction is always positive, and it's a unitless number. Okay. So, the harder that the surfaces are squished together, then the harder it is to move an object through a surface, right? It's kind of like the example I gave just a few seconds ago. If you're trying to drag a box and your brother jumps on top of the box, now it's going to be harder to push that box across the surface. Now, the mass of the box hasn't changed. The weight of the box hasn't changed. The only thing that has changed is the normal force between the box and the floor. So that means that friction is directly proportional to the coefficient of friction and the magnitude of this normal force. If I want to put this in formula form, then this would be it. This would be friction force, right? This is friction force. Depends on the coefficient of friction, which is how rough the surfaces are, times the normal force, which is how hard are the surfaces being squished together. Now, we have two different types of friction force, okay? We have kinetic friction, which is the friction force between moving objects, right? So when you drag a box across a hardwood floor and the box is moving, then there is kinetic friction between the box and the floor. And then we have static friction. This is the force of friction between objects that are not moving. So for example, if you try to push a closet and you can't move it, right? That's because, well, one, the force of static friction between the closet and the floor is too big and you can't move it. or the other one is just, you're not strong enough. But okay, that's not it. It's friction force. That is why you can't move it. It's not because you're not strong enough, because you are. All right. Okay. Now, how are these two forces different from each other? Okay. Let's think of an example. Let's say we have a desk resting on a horizontal floor. So here we have the horizontal floor, and here we have our desk. Right? Now, when this desk is here, then there are certain forces acting on it. All right? By this desk being here, just resting on the floor, I know that the desk has a mass, therefore it's going to have a weight, and the desk is resting on the floor, so there's going to be normal force acting on it. Now, suppose you push the desk. So you come here and you apply a push to this desk. Okay. Now, if this was the only horizontal force acting on the desk, then the desk should move. But suppose now that the desk does not move. Now, if the desk is not moving, that means that the desk is still at rest, which means that the desk is in a state of equilibrium, which means that the net force has to be zero, which means that there has to be another force acting in the opposite direction of this push. That way, the desk will not move and it will remain at rest. Okay? This force that we apply on the desk, okay? So we had the weight, we had the normal force, we had our push, and we have this force. Now, this force that we're applying here is what we know as, this is what we know as the force of static friction. Now, it is the force of friction, but the desk does not move. So that makes the force static, right? Because static friction is the force between objects that are not moving. Now, suppose we now increase the push and we start pushing harder, but the desk still doesn't move. Now that means that if we increase this push, but the desk does not move, then the force of static friction should also increase. Right? Just to keep these two forces balanced so that the desk remains at rest. Now, if I start to push hard enough, then eventually the desk will move. Now, when this happens, when the desk moves, then this friction is no longer static, right? This becomes now kinetic friction. Because once you start moving, then the two objects interacting are in motion, which this changes now to a kinetic friction. Now, if I look this in the form of a graph, then we would see something like this, right? When the desk is not moving, the force applied has to be equal to the force of static friction, right? This whole line is static friction. So if I push the desk with 10 newtons of force, then static friction will be also 10 newtons, right? Because the forces need to balance each other out. So if I push with 10 newtons, then there has to be a friction force of 10 newtons. If I push with 20 newtons, then friction force has to be 20 newtons. Until eventually, there's going to come a point where my push is going to be stronger than the maximum static friction. And when this happens, then the desk moves. And when the desk moves, the desk is no longer in equilibrium, right? So that means that our push is going to be this, and our friction force is going to be smaller than the push, so that there is an unbalanced force and the desk can move. When this happens, we move into this area right here, okay? Which is when the object starts to move, starts to slide, okay? Now, one thing to consider is that the maximum static friction force, which is this value right here, this is our maximum static friction. So our maximum static friction force is always going to be greater than our kinetic friction. Now our kinetic friction force always has the same value, right? It's an average, doesn't change. But static friction changes from 0 to a maximum value. All right, let's look at some examples now. So let's look at this example right here. There is a 10-kilogram mystery box resting on a horizontal floor. The coefficient of static friction is 0.4 and the coefficient of kinetic friction is 0.3. Determine the force of friction acting on the box if a horizontal applied force is exerted on it with magnitude of 0, 10, 20, 38, and 40. Pause the video here, take a couple of minutes, and see if you can come up with an answer for this. All right, welcome back. All right, let's look at this option right here. All right, so if applied force is equal to 0, then there is no force, which means that there is no friction force and the box will not move, right? So when the applied force is 0, then friction force will also be 0, right? Now, if we have, if now friction force is 10, if we apply a force of 10 newtons, then let's see what this friction force is going to be like. Now, the first thing we have to ask ourselves is 10 newtons enough to get this box moving? Okay, now to do that, let's see how much is our maximum static friction force and how much is our kinetic friction force. So I'm going to do that right here on this table. Now I know that friction force is equal to mu times normal force, right? So first I need to find normal force. Now in this case I know that my forces in y is going to be equal to 0, right? Because the box is not moving vertically, which means that normal force minus weight is going to be equal to 0, which means that normal force is going to be equal to weight, which means that normal force is going to be equal to mass times g, which is 98 newtons. Now, which now means that friction force will be equal to mu times normal force. So my maximum static friction force is going to be equal to 0.4 times 98, which is 0.4 times 98 gives me 39.2. And my kinetic friction force is going to be equal to 0.3 times 98, which is 0.3 times 98, 29.4. All right, so When the force applied is 10 newtons, 10 newtons is less than 39.2. So that means that the box will not move, which means that friction force is equal to 10 newtons. When the applied force is 20 newtons is not enough to break static friction. That means that the box is still in equilibrium and friction force will now be 20 newtons. When the force applied is 38 newtons is still not enough to overcome static friction, which means that the box is still in equilibrium, and that means that friction force is 38 newtons. Now, when the applied force is 40 newtons is enough to break friction force, which means that when the applied force is 40 newtons, the box will now move, and our friction force will be equal to the kinetic friction force, which will be 29.4 newtons. All right, let's move on to our next example. In this next example, we have two boxes connected by a cord. Coefficient of kinetic friction is 0.2, okay? And we wish to find the acceleration of this system. So we want to find the acceleration of these two boxes right here. So we can assume that the boxes move. All right, pause the video here, take a couple of minutes and see if we can come up with an answer here. All right, welcome back. Now, this type of problem can be solved in two different ways. The first way is to look at each box individually. All right, so I'm gonna look at box A right here, and I'm gonna draw a free body diagram of the forces happening on this box. All right, now this box has a mass, so it's gonna have a weight. It's resting on a surface. It's gonna have a normal force. It's being pulled by a rope, so it's gonna have a tension force, and there is friction, which opposes motion, which will be acting on the other side, right? So on box A, I know that vertically speaking, it is not accelerating, so sum of the forces in y is going to be equal to 0, which means that normal force minus weight is going to be equal to 0, which means that normal force is going to be equal to WA, which means that normal force is going to be equal to 49 newtons. And I know that the sum of the forces in x is going to be equal to mass times acceleration, because this box is accelerating. This means that tension minus friction force is going to be equal to mass A times acceleration. Tension minus friction force, mu times normal force, is equal to 5A. Tension minus the coefficient of friction is 0.2. 0.2 times normal force is equal to 5A. So now we have that tension minus 0.2 times 49 tension minus 9.8 equals 5A. Now I have two variables here, so I can't really do anything else. So now I'm going to look at box B. If I look at box B, then I'm going to have this. There's going to be weight B, and there's going to be the rope here, which is the tension. And box B is not resting on any surface or anything like that, so these are the only forces that are acting on box B. And here I know that sum of the forces in y is going to be equal to mass times acceleration, because this is moving vertically. So that means that, and since the box is moving downwards, I'm gonna do weight minus tension equals mass B times A. This means that weight 19.6 minus tension equals 2A. Now, here we have the same rope, so the tension on the rope is the same, so this tension and this tension are equal, and the two boxes are moving together, which means that this acceleration and this acceleration are also equal. So now I have two equations with two variables, and I should be able to combine these two into one equation, right? So here I have that from equation B, I know that tension is equal to 19.6 minus 2A. Then insert this in equation A, and I have 19.6 minus 2A minus 9.8 equals 5A, which means that 9.8 equals 7A, which means that the acceleration is equal to 1.4 meters per second squared. And if I wanted to solve for the tension in the rope, I can substitute this value of acceleration into this or into this number, right? And the tension would be the same. All right. Now, the second way in which we can solve this type of problem is by looking at this whole thing as a single system, as a single object moving together, which means that I have to draw all the forces acting on both boxes at the same time. So this is going to be WA, this is going to be normal force A, here I'm going to have the tension, and here I'm going to have friction force. And on box B, I'm going to have weight B, and I'm going to have tension. And then I need to assign a positive direction. So my positive direction is going to be this. This direction is going to be considered positive, okay? So now I look at all of the forces acting in this direction, and it's equal to mass times acceleration. So I start here. WB is going in the opposite, in the positive direction, so WB. Tension is going in the negative direction, minus tension. This tension right here is going in the positive direction, plus tension. And friction is going in the negative direction, minus friction force. Now, weight and normal force are not part of the motion of the two boxes, so I do not consider them on this equation. However, I do still need to prove that normal force is equal to weight. So normal force A minus WA equals 0. Normal force A equals WA. Okay, it's equal to 49 newtons. So now this is going to be this formula, right? WB positive minus tension plus tension minus friction force. This is going to be equal to MA. But which mass am I going to use? Well, since I'm looking at both boxes, as a single system, then I need to look at both boxes here. So it's going to be equal to mass A plus mass B times acceleration. So now I fill in the values. WB is 19.6, minus tension plus tension, they cancel each other out, minus friction force. Friction force we said was 0.2 times 49, so this will be 0.2 times 49 equals mass A plus mass B times A. 19.6 minus 9.8 equals 7A. 9.8 equals 7A. A is equal to 1.4 meters per second squared. So same result, right? You can choose whichever method you like best. They're both work, they're both the same, okay? All right, let's look at one more example here. So your little sister wants a ride on her sled. You are on flat ground and you are thinking about either pushing or pulling on the sled at the same angle, all right? Which way would you exert less force? Pause the video here, take a couple of minutes and see if you can answer this one. All right, welcome back. Now, when looking at this, the first thing that we need to do is, of course, draw a free body diagram. So on A, situation A, we'll have the sled here. You're pushing, so let's say you're pushing, so we can draw the force this way. You'll have the weight, you'll have normal force, and let's say there's friction force, okay? So we'll have friction force acting in this direction. On option B, we'll have the same sled, we have weight, we have normal force, and we have F in this direction, and of course, friction force. So the question becomes, in which example, either pushing or pulling, where is friction force smaller, right? Because why do we only look at friction? Because here, right, if we look at each free body diagram, Fx, our horizontal force, is the same on both examples. So our Fx will be the same because F is equal and the angle is equal. So the horizontal force will be equal on both cases, which means that it's going to be easier to push if friction force is less. Now, friction force depends on two things, the coefficient of friction and normal force. Our coefficient of friction is the same because it's the same sled on the same surface. So it all comes down to normal force. In which option is normal force less? Well, in option A, if I do a sum of the forces in Y, I will have that normal force is going to be equal to weight plus Fy. And here in option B, I'm going to have that normal force plus Fy is going to be equal to weight, which means that normal force is going to be equal to weight minus Fy. So on this case, in option B, normal force is less, which means that friction force is less, which means that you'll get less tired and you will exert less force. All right. Thank you all for watching. See you next time.